evening, everyone. This is Vikas Srivastav again. So I hope you all are having a great time, right? So yesterday we started learning about linear algebra, and the first topic that we covered was vector algebra, right? So we learned about vectors. We learned about some operations that we can do on vectors. Also learned about some of the properties of those vectors, right? And so today we are going to learn about the continuation of the previous topic in a way. Uh, so the topic for today is matrix algebra, right? So I guess you all must be familiar with the concept of matrices, right? So we all covered and in fact introduced you to the idea of a matrix when we are learning NumPy, right? So you have this idea that a matrix is a two-dimensional uh, array of numbers, right? So uh, a matrix has columns and rows, etc., right? So you know this from the previous classes, and also I think in your 11th and 12th I do hope that you have learned about the theory of matrices, and today we are going to essentially revise and revisit those concepts, and later on in our machine learning classes we'll be leveraging these ideas, these fundamental concepts, so that we can understand those algorithms in deeper detail. Okay, so as you all know, a matrix A is defined as a data which is arranged in m rows and n columns, right? So whenever we say that a matrix is a set of data or numbers arranged in m rows and n columns, we say that the order of this matrix is m cross n, right? So let's say if this is a 3 cross 3 matrix, so it has 3 rows and 3 columns. Okay, and so each element of the matrix can be denoted with a very useful notation that we can use. So Aij, right? So I tells us the row and J tells us the column, right? So if you want to point to a particular element of this matrix, so you need to specify the row and you also need to specify the column. Okay, so so for example, if we talk about this 2, right? So this is the first row and the first column, right? So A11 will be equal to 2. Do not confuse yourself with the notation that we have learned in Python, right? So there, let's say if you are talking about indices, so you know that indices in Python they start from 0. So you don't have to confuse for this element, for example, this particular 2. So you don't have to say that A00 is 2, but essentially we'll be using the normal natural number sequence whenever we want to refer or point to a particular element in the matrix, right? So A11 is 2 because 2 is sitting in the first row, right? So this is the first row and this is the first column. Okay, if I wanted to locate the element -6, so I would need to go to the second row and of course the second column. Okay, similarly, let's say if I wanted to refer to this particular element -2, I would have to go to the third row, and I'll also need to look at the second column, right? So this -2 element sits at the third row and in the second column, right? So when we specify these two parameters or these two values, so we're able to refer to a particular element in the matrix, right? So of course, in this particular case, this matrix is has the same number of rows and the same number of columns, but in general a matrix can be represented as m rows and n columns, where m and n can be different as well. Okay, so this is the basic idea of matrix and the basic definition too, right? So each element can be denoted with this notation Aij, where I refers to the row number and J refers to the column number. Okay, and do not confuse yourself with the concept of indices which you have learned in Python, right? So here we are not talking anything related to Python. We are just focusing on the mathematical concepts, right? So just be cautious. Okay, so I can provide new data, and as you can see that let's say if I have new data, so this particular element 9, so this is A33. Okay, -6 will be A13 because this is the first row and the third column. Okay, so this is how we essentially construct a matrix, and we can refer to the elements of this matrix in such a way. Okay, so let's move ahead. So let's move to the types. Okay, so there are different types of matrices. So the first matrix is let's say column matrix. Okay, so column matrix is of order 3 by 1, right? So in this example, of course, this is 3 by 1, but the important thing is in a column matrix you'll only have one column, but you can have as many rows you want, right? So this is an example of a matrix, a column matrix, in fact, which is of order 3 cross 1, where we have 3 rows, right? So as you can see, 3 rows, and we just only have one column. Okay, so this is a particular example of column matrix, but you can also have 5 cross 1 order column matrix in which you'll have 5 elements but only one column, right? So this is what we refer to as the column matrix. Okay, and then we have the concept of row matrix as well. So in this case, the order will always be 1 cross some number, right? So this number 3 is fixed, this number 1 is fixed for row matrix, because in a row matrix we'll only have a single row, but we can have as many columns as we want, right? So in this example we have 3 columns, right? So this one column, this is the second column, this is the third column, but the number of rows in this row matrix will always be 1, right? Just as similar to the case of column matrix. In the column matrix we fix the number of columns to be 1, but we can have as many rows as we want in our column matrix. And similarly in the row matrix we can will be fixing the number of rows to 1, but we can have as many columns as we want, right? So these are the basic type of matrices. Let's look at another type of matrix, which is symmetric matrix. I think, yeah, I forgot the brackets here, but I hope, yeah, you guys understand, but I can of course annotate this. Okay. All right, so this is a symmetric matrix. So what is a symmetric matrix? So symmetric matrix is that matrix in which Aij will be equal to Aji, right? So essentially, so Aij, this element is sitting at the ith row and jth column, right? So let me just write the definition of this symmetric matrix. So maybe what I can do. Okay. So here, so I can have, so the definition is basically Aij is equal to Aji. Okay, so just look at this particular matrix. Okay, so let's look at this particular element, which is 2. Okay, so what is I in this case? So I is 2 and j is 1. Okay, so A21, so right, so this is A21, right? Now for a symmetric matrix we need to have this condition that Aij is equal to Aji. In this case, what does that mean? That A21, in fact this will be applicable for all the elements of the matrix, but I'm just trying to take an example here. So by this definition, so A21 should be equal to A12, right? So which is A12? So we'll go to the first row and the second column, right? So this is that element, right? So in this case we have these two elements which are 2 and they are equal, right? And as you can verify, so this is A13 and this element is A31, right? So both these elements are equal. Also, if you look at this particular element, so this is A23, right? So this element is A23, and if you look at this element, so this is A32. Okay, so both these elements are equal. So this is a symmetric matrix. And of course, if you look at the diagonal, so if you look at these diagonal elements, so these are 1, 4, 6. So essentially for them the row number and the column number both are identical, right? So A11, or right, so essentially if you flip the order of the row and the column, it's essentially is the same, right? So A11, A22, A33, all these elements are of course sitting in the diagonal. And yeah, so this does not matter in this case, but of course we'll need to look at the other elements which are not sitting in the diagonal. Okay, so just to repeat again, so these elements which are sitting in the diagonal, so these are the diagonal elements, right? And here of course we have A11 is equal to A11, right? And if you look at the non-diagonal elements, so there we are getting this condition fulfilled for other elements, right? So this particular condition, which is Aij should be equal to Aji for all the i's and j's of this matrix, right? So in this particular case of 3 by 3 matrix, I can take values from 1 to 3, right? And then j can also take values from 1 to 3. Okay, so in this case, yeah, it will be a symmetric matrix. Okay, so so this is an example of symmetric matrix. Now, so now if you look at the anti-symmetric matrix, so in this case, I think you should be able to figure out. So Aij will be equal to minus Aji. Okay. So now if you look at this particular element, so this is A12 and this particular element is A21, and as you can see, both so they are not equal, but essentially A12 is equal to A minus A21, right? So this is a anti-symmetric matrix. Okay, and as you can already guess, why the diagonal elements are 0, right? So if I try to validate this condition, so let's say if I want to talk about this particular element, which is A11, right? So by the condition, we should have A11 equal to minus A11. Okay, so in this case, what we'll have, so 2A11 is equal to 0. That means A11 will be equal to 0, right? So in the case of anti-symmetric matrix, by the very definition, you're given that, yeah, the diagonal elements are going to be 0, right? So as you can see, all the diagonal elements will be 0. And if you look at the non-diagonal elements, so for example, this A13, sorry, this will be A31, in fact, right? Right, so A31 and this element, which is A13, right? So they are not equal, but A13 is equal to minus A31, and or vice versa, right? A31 is equal to minus A13, right? So in the case of anti-symmetric matrix, the basic definition for each element or any element of the matrix would be this particular condition, right? So Aij will be equal to minus Aji, right? So this is the basic definition you need to remember. Okay, and okay. So now, so what do you? So here we have been talking about the matrices for which the number of rows is equal to number of columns. Okay. Now let's talk about. So let's say if I add a few elements here, right? So something like 9, 7, 8, right? So here this element. So now this is not a matrix in which we have equal number of rows or equal number of columns, right? So this matrix is of order 4 cross 3, right? So we have 4 rows and 3 columns. So 9, this element 9 is essentially A41. But what about A14, right? Now, does this element exist in this case, A14? So you guys can mention over the chat. So does this element exist? A14, right? So the element sitting in the first row, but the fourth column, right? Right, so it does not exist exactly, right? So in this case, what we'll say that the idea of symmetric matrix and anti-symmetric matrix will make sense when we have what we call a square matrix, right? So square matrix is nothing but a matrix in which the number of rows and the number of columns, they are identical, as in the order whenever we refer m cross n, so m is equal to n. Okay, so yeah, just give me a second, guys. Okay, all right. So this is the idea of symmetric and anti-symmetric matrix. Okay, can you guys please confirm over the chat if you are able to understand this concept of symmetric and anti-symmetric matrix? Okay, just let me know. All right. Okay, so that's great. All right. Okay, so now we'll move forward. Okay, so now let's look at other type of matrices. So I'll just drag this slider. So now we have so now there is another matrix which is called as null matrix, right? So a null matrix is a matrix of any order, right? So not necessarily it has to be square. Okay, so let me just let me see if I have the square matrix here. No, okay. So I have not defined the square matrix, but that is really important. So I'll just give you the idea, right? So let's say So if you have any matrix in which, so let's consider a matrix A, and this is of order. So this sign is sort of equivalent, right? So let's say this is of order uh, m cross n. Okay, m cross n. So for a square matrix, there is a condition that m is equal to n. Okay, so your number of rows has to be equal to number of columns, right? So essentially any matrix of order 2 cross 2, 3 cross 3, 4 cross 4, 5 cross 5, so all these are square matrices, right? But any such matrix for which you don't have m equal to n, so that will call as non-square matrix. Okay, so this is the basic definition, and we'll be using the concept of square matrices because there are a lot of other important concepts in linear algebra which only, in fact matrix algebra, which only applies to square matrices, right? So that's why I thought, yeah, you should have this particular idea if you do not if you don't know about it beforehand. Okay, so now let's talk about a null matrix. So null matrix is essentially a matrix of any order. Okay, so in this case, what is the order? So the order is simply 3 cross 2. Okay, so this is a matrix of order 3 cross 2, and all the elements will be 0. Okay, so all the elements of this matrix will be 0. So this is called a null matrix. Okay, now moving on to another matrix. So yeah, just give me a moment, guys. So the another matrix is what we call as identity matrix. Okay, so it is a really important matrix, and I think uh, so this matrix is in a way matrix equivalent of number 1. Okay, uh, or in normal arithmetic or normal algebra, we let's say if I multiply any number by 1, so that number will be 1, right? So essentially this identity matrix is in a way equivalent of the number 1 but in matrix, right? So what is the property of this identity matrix? So all the diagonal elements are 1. Okay, so all the diagonal elements are 1, but uh, all the non-diagonal elements are 0. Okay, so this is the definition of identity matrix, and of course identity matrix is a square matrix. Okay, so this is really important. So identity matrix has to be a square matrix. Okay, so let's say this is I3 because this is of order 3, right? Because we don't have to write I3 cross 3, because here whenever we talk about a square matrix, it's already known that, yeah, the number of rows will be equal to number of columns. So we just need to specify one particular parameter, right? So in this case, I3 is this 3 cross 3 matrix in which all the diagonal elements are 1, but all the non-diagonal elements are 0. Okay, so similarly we can have I2 in which we can have 1 0 0 1. Okay, and then of course you can have I4, that will be a 4 cross 4 matrix, and all the diagonal elements will again be 1s, and all the non-diagonal elements will again be 0s. Okay, so now moving ahead, so this is diagonal matrix. Okay, so a diagonal matrix is that matrix in which we have the elements populated along the diagonal. They're not necessarily 1 as was the case with the identity matrix, but in the case of diagonal matrix, what will be the case? That the diagonal elements will be non-zero, but all the non-diagonal elements will be 0. Okay, so that is the basic difference between your identity and diagonal matrix. So in your diagonal matrix, you can have all the elements along the diagonal. They can be different, right? So we can have 1 2 3 in the diagonal, but your non-diagonal elements, they have to be 0, right? So that's the basic definition of diagonal matrix. Okay, so now moving ahead, so now we have this concept of upper triangular matrix. So this is again a pretty straightforward matrix. So as you can see, so if you look at the upper triangular part of this matrix, so uh, so these are non-zeros, but the lower ones, so these are zeros, right? So this is the definition of upper triangular matrix. So your upper triangle will be non-zero elements, but the lower triangle, that will be zeros. Okay, so that's the definition of upper triangular matrix. And similarly, we have this idea of or the concept of lower triangular matrix, in which the lower triangle, which is this one, right? So these are non-zeros, but if you look at these elements, so these are zeros. Okay. So in the lower triangular matrix, the lower triangle elements or lower triangular elements, they are non-zeros, but the uh, but all the elements apart from it, they are zeros. Okay. But in the case of upper triangular matrix, uh, the upper triangular elements, they are non-zeros, but rest of them are zeros. Okay. So this is the basic definition of upper and lower triangular matrices. Okay. One important concept which is not related to mathematics, uh, but okay, I'll just cover that later. Okay, so the next matrix is scalar matrix. Okay, so scalar matrix will have the same elements along the diagonal. So this is essentially, if you multiply this identity matrix with number 5, so you'll get the scalar matrix. Okay, so I'll talk about the multiplication of matrices with a number with another matrix, etc. So there are some certain rules which you need to follow, but for now, to understand the concept of scalar matrix, just keep this in mind, that all the diagonal elements will be equal. Okay, they do not necessarily have to be one. So in that case, that scalar matrix will be identity matrix, or you can say that a specific scalar matrix in which the diagonal elements are one, that is an identity matrix. Okay, so in a scalar matrix, your diagonal elements will be non-zero, of course, and they will be the same, and all the non-diagonal elements, so those will be zero, right? So non-diagonal elements are this, right? So everything apart from your diagonal elements, right? So this is the concept of scalar matrix, right? So let me know if you guys are able to understand these matrices. Just let me know over the chat, right? So okay, so these are pretty straightforward concept, and I'm pretty sure that you guys have already studied these things in your class 11th and 12th, right? But anyways, I'm just revisiting over these concepts so that yeah, you get an idea of what we are going to learn and apply. All right, so let's move ahead. So now uh, we have this concept of uh, transpose of a matrix. Okay, so here, of course, I just wanted to, yeah, just check with new data sets. Okay, so now if you can experiment on your own whenever you have time, right? So you can just click on this new data, and yeah, the elements will be updated according to a logic, and you can verify these things, right? Right. So a scalar matrix is essentially a unit matrix multiplied by a scalar, right? Because I have not yet discussed the scalar multiplication, right? So we are not yet up to the point where we're discussing multiplication. So that's why I didn't specify this particular point. But of course, a scalar matrix is just a unit matrix multiplied by a or identity matrix multiplied by a scalar. Okay. Smoothie is asking, can a 3 by 3 null matrix be called diagonal matrix? That's a pretty interesting question. I think so. In the case of diagonal matrix, all the elements will be non-zero. Okay, so so in that case, yeah, it will not be a null matrix, right? So your diagonal elements have to be non-zero. They are not necessarily equal, all these elements, right? So as you can see, is either 8, -5, 3, right? And these elements will be different, but they will not be equal to zero. Okay, so I hope you got your answer. Okay, all right. Okay, so let's move ahead. So we were discussing the concept of a matrix transpose. So it's pretty straightforward. So let's consider this a 3 by 2 matrix, right? So we have 3 rows, as you can see, and we have 2 columns in this case, right? So this is a 3 cross 2 matrix. Okay, so whenever we transpose a matrix, we are essentially interchanging the rows and the columns. Okay, so our rows will become the columns and our columns will become the rows, right? So in this case, -2, -1, -3 is a column. So when we transpose this, this particular column will become a row. Okay, so this will be a row here, as you can see, -2, -1, -3, and then this particular column, which is -1, 0, -8, this will again become the row after we transpose this. Okay, so this will be -1, 0, -8, and as you can see, the order of the matrix has changed. Of course, we're transposing here. So in this case, the rows of your original matrix, becomes the columns of your transpose matrix, and similarly the columns of your original matrix becomes the rows of your transpose matrix. Okay, so this is a pretty straightforward concept, and I think yeah, you guys should be able to understand the concept of matrix transpose. So essentially interchanging the rows and columns. Okay, so I guess yeah, you guys are able to understand the concept of matrix transpose. Okay, so let's move ahead. So now, up till now, what we have discussed, so we have discussed the basic definition of a matrix, and we have discussed different types of matrices, right? So now we are ready to do some arithmetic operations on the matrices, and let's start with the addition and subtraction. Okay, so let's say I have these two matrices, right? And of course, I can annotate here. So this is, of course, I'm sorry. Right, so this is a 3 by 3 matrix, and this is again a 3 by 3 matrix, right? So needless to say, whenever I give you a matrix, you can of course always tell the order of that matrix. Okay, so here, let's say if I want to add these two matrices, so how do I do that? Okay, so let's do this particular step. In fact, yeah. Okay, so okay, so let's sum these two matrices. So as you can see, both are of order 3 cross 3. Okay, so when I click on this button, right, which is sum the matrices, so so the first element will be 7 plus minus 9. Okay, the second element will be 4 plus 1, right? So essentially we're adding the corresponding element of these two matrices. Okay, and then we have 5 plus 0, and then of course this element will be minus 7 plus 0, 5 plus 9, 2 plus 1. Okay, and 0 plus minus 7, and then minus 7 plus minus 2, and then 0 plus minus 3, right? So this is what we get when we try to add these two matrices. And as you can see, so this is minus 2, this is 5, this is 5 again, minus 7, 14, 1, and minus 7, minus 9, minus 3, right? So in this way, so whenever we want to add two matrices of the same order, right? So we'll essentially add the corresponding elements. Okay, so a, let's say this is a11, this is b11, right? So a11 plus b11 will give us c11, which is your resultant matrix. Okay, similarly we'll add all the elements, so all the corresponding elements. Okay, so there is one important concept here. So these two matrices cannot be added because they are not of the same order, right? So the order of the matrices are really important here. Okay, so both the matrices should be of the same order. Okay, that's when we'll be able to add the corresponding elements of these two matrices. Okay, so and you can check with the new data as well, right? So it's essentially the same thing, right? So 9 plus 4, 8 plus 2, and then minus 4 plus minus 9, right? So in this way we can add the two matrices. Okay, similarly, right, so addition or subtraction, they are essentially the same operation, right? So I can have minus here, so essentially instead of plus operator we'll have the minus operator. Okay, so addition and subtraction, they're essentially the same thing, and instead of plus we'll have minus whenever we want to subtract two matrices. And in whenever we're subtracting two matrices, we need to make sure that the order of the both the matrices, they have to be same. Okay, so now let's move ahead. So we can now discuss the concept of first of all, yeah, before I move ahead, I think yeah, you guys are already comfortable with this particular addition and subtraction, right? So now yeah, let's move ahead. So the product of two matrices. Okay, so now I have this matrix. Now let me just annotate this and write the order here. So this is of course 3 cross 3. Okay, so this is a 3 cross 3 matrix, and we are ready to yeah, multiply them. So now what I am doing here, so I am basically multiplying this matrix by a number, okay, or by a scalar, right? So you know that a number is also referred to as a scalar. Okay, So let's say if I want to multiply this matrix with a number 7, right? This could be any number, but in this case, yeah, I've taken an example of 7. So let's multiply this, right? So what will happen? We'll have to multiply each element by this number or scalar, right? So as you can see, so each element of our matrix is being multiplied by that same scalar quantity, and this is our final resultant matrix. Okay, so this is an example of scalar multiplication in which we are multiplying a matrix by a scalar quantity. So whenever we do so, what we'll do, so our resultant matrix, so all the elements of the resultant matrix will be obtained by multiplying the scalar with all those corresponding elements, right? So this is what we'll call as scalar multiplication, right? So now let's move ahead. Let's talk about product, right? So this is a really important concept, and yeah, I'll spend some time here on this. Okay. So of course, yeah, let me just, yeah, so of course, yeah, we'll talk about the properties of addition later on, but for now what we'll do, we'll see how we can multiply two matrices. Okay, so in order to multiply two matrices, the number of columns in the first one must be equal to the number of rows in the second one. So this is pretty important point, right? So the number of columns in the first one. Okay, so what does this mean, right? So let's consider this particular matrix, which is a row matrix, right? So a row matrix, so this has the shape, or sorry, the order 1 cross 3. Okay, and this particular column matrix has the order 3 cross 1. Okay, so let's see in this case if this criteria is being satisfied or not. So the number of columns in the first one, right? So 3 columns must be equal to the number of rows in the second one, right? So the number of rows in the second one is again 3, right? So in this case, we can multiply these two matrices. Okay, so the result of multiplying them is a number that is obtained by adding the products of the elements that occupy the same position. Okay, so let's look at this particular example, and yeah, you'll get the idea. Okay, so now you know that these two matrices can be multiplied just because of this very basic property, that the number of columns of the first matrix or the left matrix must be equal to the number of rows of your second matrix or the matrix on the right hand side. Okay, so now let's multiply them. So what we'll do, we will multiply each element and then add them together. Okay, so 9 multiplied by -3 plus 8 multiplied by 5 plus -4 multiplied by 9. Okay, so now this gives us -23, right? So in this case, when we multiply a row matrix with a column matrix, we get a simple number, right? But I think you guys already know this from before, but just for a recapitulation, you should yeah, you will be able to agree with me in this case, right? So we are getting this particular number, right? So now let's yeah, slide. Okay, so now let's talk about these two matrices. So are they, can we multiply these two matrices? Okay, so one important thing is, so let's say you have a matrix which is a matrix A of order m cross n and a matrix B of order n cross p. Okay, so maybe I can write it for you in detail here. So let's say I'll write in top. So matrix A of order m cross n. Okay, now you're multiplying this. Do not confuse this with a dot product, what we have discussed in vectors, right? So here there's no such concept of dot or cross product. Okay, so we're simply just multiplying them. Okay, so we'll denote them with this particular dot only. Okay, so but that idea is not valid here. Okay, so this is a matrix A of order m cross n, and then you have this matrix B of order n cross p. Okay, so remember in the previous slide we learned that, yeah, these two matrices are multipliable because this number is equal to this number, right? So the number of columns in the first matrix must be equal to the number of rows in your second matrix or the matrix on the right. Okay, and what will be the shape of the resultant matrix? So the shape of the resultant matrix will be C M cross P. Okay. So the number of rows in our resultant matrix will be M, and the number of columns in our resultant matrix will be P. Okay. So very simple, right? So you just need to verify if these two matrices are multipliable. They will be multipliable only in this case where these two numbers are equal, right? And what will be the order of the resultant matrix? So the resultant matrix will have m number of rows which will come from the first matrix, and p number of columns which will come from the second matrix. Okay, so the order of the resultant matrix will be m cross p. Okay, so remember in our earlier example, when we took a row matrix and a column matrix, we multiplied them, right? So our resultant matrix was just a single number, right? So that we can refer as C1 cross 1, right? So maybe I can write it over here. So earlier what we did, we multiplied 1 cross 3 with 3 cross, right? So we multiplied with 3 cross 1. Okay, so in this case what we got, so our final matrix, so that was of course a number, but we can tell that we can denote that number as a matrix of shape or order, let's say C1 1 cross 1. Okay, because it is just a number, so it has just one row and one column. Okay, so I hope you are familiar with the matrix multiplication rules. Okay, so can you guys please confirm over chat if you are able to understand the matrix multiplication rules and how are we getting the order of the resultant matrix? Okay, perfect. All right. So let's multiply these two matrices. Okay, so I have in this case a matrix of order 3 cross 2, and then I have this matrix 2 cross 2. Okay, so now as you can see, yeah, these two matrices are multipliable because these two numbers are the same. Okay, and what will be the shape of the resultant matrix? So it will be 3 cross 2. Okay, so let's multiply the matrices. So minus 3 will be multiplied by 9. Okay, and this element will be, and then plus minus 7 into 5. Okay, so my resultant matrix will be of the shape, of course, 3 cross 2. Sorry, 3 cross 2, and the first element. Okay, so the first element will be calculated by multiplying minus 3 with 9 plus minus 7 into 5. Okay, so essentially we're covering one row here, and then multiplying this with the corresponding elements in the first column of the second matrix. Okay, so this is how we get the first element of our resultant matrix. Now let's move ahead. So the next element will be given by this particular row, but the second column, right? So minus 3 into 8 plus minus 7 into 7, right? So this will give us the second element of our resultant matrix. Okay, so now let's move ahead. So this element, which is essentially a 2 1, that will be given by multiplying this row with the first column, right? So minus 2 into 9 plus 3 into 5. Okay, so this is how we get the this particular element, which is sitting at the second row and first column. Now let's talk about this particular column. So again, here we'll multiply with the same row, but now here we have the second column. Okay, so minus 2 into 8 plus 3 into 7. Okay, and similarly we can get these elements by multiplying the third row with the first column, and then this element will get by multiplying the third row with the second column. Okay, so now let's see. So this is a matrix, this is a resultant matrix, and as you can confirm, so this matrix is of the shape 3 so 3 cross 2. Okay, so we have 3 rows and 2 columns, and that's coming from essentially here, right? So this basic rule which I have discussed. So how will you get the order of the resultant matrix? So the number of rows will come from your first matrix, or the matrix on the left hand side, and the number of columns will come from the matrix on the right hand side, okay, or the second matrix. Okay, so this is how we get these two, we multiply these two matrices. Okay, So now let's move ahead. Okay, so now we are ready. So let me, yeah, just okay. So now we know that how we can multiply two matrices. Okay, and you know when are two matrices multipliable and what will be the order of the resultant matrix, right? And you can of course calculate each element because I've told you the rules, right? Now let's look at some of the important properties of the matrix multiplication of matrices. Okay, so first important property is the product is not commutative. So what is the meaning of commutativity? So here when we say a dot b, or when we multiply two matrices, a multiplied by another matrix, so this is not equal to in general b dot a. Okay, so let's consider this example. Okay, so in this example I have this matrix on the left hand side and this matrix on the right hand side. Of course, these two matrices are multipliable because this is again 2 cross 2 and this is also 2 cross 2. So these two matrices are multipliable and we get this particular final resultant matrix. But if I move this matrix on the left hand side and I move this matrix on the right hand side and multiply them, so my resultant matrix, as you can see, these are not equal, right? When we say that two matrices are equal, so if their corresponding elements are equal, then only we'll say that those two matrices are equal. Okay, so let me just write. Okay, so matrices are, in fact I should write two matrices are said to be equal. They are said to be equal when, so let's say two matrices which are a comma b, right? So these are two matrices. So let's say each element of a can be denoted by aij, and each element of b can be denoted by sorry, bij. Okay, so if this condition holds for all the elements, if this condition holds for all the elements of both the matrices, as in their corresponding elements are equal, then only we'll say that yeah, two matrices are equal, right? And in this case you can verify that these two matrices are not equal. Okay, so so the basic property of the product of two matrices is non-commutativity. Okay, as in if you flip the order of the matrices when you're multiplying them, so the resultant matrix might not be equal. Okay, so there could be some special cases in which we'll see that yeah, even if we change the order, the resultant product is the same, but that is not the case in general. Okay. Okay, all right. So can you please confirm if you are able to understand the property of commutativity? Okay, perfect. So now let's move to the second property. So I'll just move this slide. So this is how you can essentially experiment with this GeoGebra applets. Okay, so these are available in your course dashboard. So this is how you have to operate, right? So firstly, you need to focus on this particular slider, and then when you have this product property, so you can move these sliders to get all the properties, right? So this is how you have to play with this particular applet. Okay, so now this is another important property. So this is the property of associativity. Okay, so the product is associative. Okay, so let's say if I multiply these two so I have three matrices which I want to multiply. So I multiply these two matrices first, and then whatever the resultant matrix is, I multiply this with C, which is another matrix C, right? Now in another case, so I multiply B and C firstly, and then whatever the resultant is, I multiply it with A. Okay, so in this case, the resultant of the product of these three matrices will be equal. Okay, so this is an example for the demonstration of the very same concept. So here I've considered three matrices A, B, and C. And if I multiply A, B first, so I'll get this particular matrix, and I multiply with this C matrix. Okay, and I get this particular resultant matrix. Okay, and in this case, I multiply B and C together. So I get this particular resultant matrix first, and then of course, I have A on the left hand side. Okay, and I multiply them together, so I get this resultant matrix. And as you can see, both these matrices are equal because each and every corresponding elements of these two matrices are equal. Okay, so you can check with the new data. I think, yeah, this is not working for this case, but of course, yeah, you get the idea of the concept of associativity. Okay, so let me know if you have any confusion, or else you can, yeah, just drop a yes over the chat so that I can, yeah, I know you guys have understood this concept. Okay, so all right. Okay, so this is a pretty straightforward concept. So let's say if you're multiplying three matrices in order, okay, A, B, C. So I can first multiply A and B together. So I get a resultant matrix because, of course, whenever you are multiplying, let's say you have four matrices to multiply, right? A, B, C, D. So of course you will multiply them in certain, you will first pick any pair and then multiply, right? So that is how you're going to start, right? So you'll start with multiplying two matrices, and then you will multiply with the rest, right? So in this case, the associativity rule holds for matrices, right? So A, B, C will be equal to A multiplied by B, C. Okay. So now let's move to the third property. So the product is distributive. Okay, so this is the property of distributivity. What it means, so let's say I have this particular matrix, right? So A plus B, right? So this is a particular resultant some matrix, and then I'll multiply this with C. Okay, so this operation is equivalent to multiplying A with C and add plus multiplying B with C. Okay, the order is important. Okay, so you need to make sure, so you cannot write CB here. Okay, so just you have to keep this in mind. Okay, so the product is distributive. Okay, so the product is essentially distributed over this operator. Okay, so AC and then plus BC. Okay, so the product is in a way distributed over both the elements. Okay, and then similarly, if you have A multiplied by B plus C, so this again will be distributed over the two elements. So A dot B plus A dot C. Okay, so the product is distributive, and again here I've taken the example of three matrices, and let me see. Yeah, this is not working in this case, but yeah, this is for demonstration purpose only. So as you can see, A plus B. So I have added these two matrices here. So A, as you can confirm, A plus B is nothing but this particular matrix, and then I am multiplying by C, and I get this final resultant matrix. Similarly, I can I can multiply AC together, so I'll get this matrix. I'll multiply BC together, so I'll get this matrix. If I add them together, I'll get this matrix. And as you can see, these two matrices are one and the same. Okay, so this is the property of distributivity. Okay, so now let's move ahead. So the fourth property is, so suppose if we have two matrices A and B, and their product is a zero matrix or a null matrix. Okay, so it does not mean that A is equal to B is equal to 0. Okay, so let's say if I have these two matrices and their product gives us a null matrix. Okay, so essentially I can tell you here, so this is of course a 2 cross 2 matrix, and this is again a 2 cross 2 matrix. So of course O is a short notation for a null matrix. This is equivalent to writing 0 0 0 0. Okay, so this is again a 2 cross 2 null matrix. Okay, and this is a shorthand notation to denote the same, right? So you don't want to write 0 all the time, right? So you can write simply 0, or essentially it's written in a curly fashion. Oh, okay. So if we multiply two matrices and our resultant matrix or the product is a null matrix, it does not mean that A or B, they are both either of them is a null matrix. Okay, so this is the particular property. Okay, so I hope, yeah, you guys understand this particular concept. Okay, so let's move ahead to the next property. So let's say if you are given this condition, so let's consider we have three matrices A, B, and C, and suppose for these three matrices you have A dot B is equal to A dot C. That does not imply that B is equal to C. Okay, so that does not imply B is equal to C. So here I've taken an example. So I have this matrix A, I have this matrix B, I have this matrix C. So A, B and AC both are equal to this particular matrix. Okay, so that means this particular condition is there, but we can conclude from this, we cannot conclude that B is equal to C, right? As you can see that B and C are not equal. Okay, so this is a really also important property. So whenever, let's say, you have this particular scenario in which AB is equal to AC, that does not imply that B is equal to C. Okay, so this is the fifth property. And the last property is, so in fact, this it's not is the penultimate property. So there is the unit element I which fulfills AI is equal to A. Okay, so let's say if you multiply any matrix with identity matrix, either that identity matrix is on the left hand side or on the right hand side, uh, it essentially leaves the matrix unchanged. Okay, so I can just take an example in this case. So suppose I have sorry, yeah, so let's say I have this matrix 2 1 1 4. Okay, and I have this identity matrix which is this. Okay, so you can confirm, right? So let's see what we get. So 2 into 1 plus 1 into 0, right? So this is 2. 2 into 0 plus 1 into 1, that is 1. Then 1 into 1 plus 4 into 0, that is 1. And then 1 into 0 plus 4 into 1, that is again 4, right? So these two matrices are the same. Okay, so if you multiply any matrix with identity matrix, so here of course I have this identity matrix on the right hand side, but even if you move it to the left of this any matrix, the resultant product or the resultant matrix will be that same matrix. Okay, so this unit element or the identity matrix, when we multiply any matrix with this identity matrix, it essentially leaves that matrix unchanged. Okay, it's equivalent to multiplying any number with this number 1. Okay, so let's say 4 into 1 is 4, 9 into 1 is 1, right? So whenever you multiply any number with 1, that it does not change that number at all. Okay, so here also in this case, if we multiply any matrix with the identity matrix, that matrix will remain unchanged. Okay, so so the last property, of course, these are not exhaustive set of properties, but I thought, yeah, guys should be able to, yeah, at least remember these properties, which are pretty important. So square matrices can have an inverse element. Okay, I'll come back to this particular point at later on. Okay, so we have not yet discussed about the inverse of a matrix. We'll come back to this particular property later on. Okay, so just hang on with me. I'll cover this particular concept, but yeah, towards at later part. Okay. So can you guys please confirm if you're able to understand these operations and these type of properties which I've discussed till now? Okay, perfect. So let's move ahead. So now we'll talk about the concept of determinant. Okay. So determinant is a really important concept. So for this also I have another interesting applet for you guys to show. Okay. So I'll not discuss the star method. So this is not required. I'll only discuss the diagonal method. Okay. So let's say I have, let's say this particular matrix, and I want to calculate the determinant. Okay. So determinant is a measure, essentially determinant is a value. Okay, it's essentially a number, right? So whenever you write, say, determinant of a matrix, so it is essentially a real number only. Okay, and so there is a particular way to calculate the determinant, and determinant has a lot of fascinating properties, which I don't think we should be able to discuss today, but of course we'll be using this whenever we want to, yeah, do some operation, or there will be concepts in which the idea of determinant is really important. Okay, so let's multiply this. Okay, so the first step is, okay, so the first step is okay, so one sec. Okay. Okay, so what you need to do, so of course I know, yeah, you guys have remembered from earlier, right? So let's say if you want to calculate the determinant in this case, so you know from earlier, right? So we can write this as 3. Okay, sorry, I need to change the uh, yeah, color of this. So okay, and yeah, so you know from earlier that this will be 3 into minus 4 minus 1 into 1, right? So essentially we look at this particular number, multiply with this, whatever we get from here. Okay, and then of course you look at this particular number and then you focus on the other two. Okay, right? And then you and then the third element will be this particular number multiplied by whatever you are getting from these four numbers. Okay, so this I think you already know from earlier, but let's discuss the Diagonals method. That is essentially a very similar way to calculate the determinant. Okay, so here what we have. So firstly, what we'll do, we'll copy these. What we'll do, we'll copy these two rows, right? So these two rows, we'll copy them here first. Okay, so we'll copy them here. So what we'll do next, yeah, so we multiply all these numbers together, and so that number is 3 into 3, that is 9, into minus 4, that is minus 36. Next, so we multiply these three numbers together, 2 into 1 into minus 4, and then write them here, minus 8. Okay, then the third is 1 into minus 2 into 1, that is minus 2 again. Okay, so the next step is, now we look in this direction. Okay, so 1 into 3 into minus 4. So here, of course, we multiplied in this fashion and stored them together. Okay, so now when we move next, so we'll of course add a minus sign here, and everything what we'll get, we'll write them in the brackets here. Okay, so 1 into 3 into minus 4, that's minus 12, and then we'll have again, as you have guessed, 3 into 1 into 1, so that is again 3, and then you have 2 into minus 4, so that is again plus 16. Okay, so whatever we get, so will be the determinant of this matrix, right? So this is how we calculate the determinant of the matrix. Of course, you know about the previous method which I discussed in the beginning, but this Diagonals method is also a very interesting way to calculate the determinant of a matrix. Okay, so any confusion about calculating the determinant of a matrix? Right, so okay, so does this diagonal method apply for higher order square matrices as well? Yes. Okay, so essentially this is the same thing which you will do. So suppose you have a 4 by 4 square matrix, so there also you will multiply this with the uh, determinant of the that 3 by 3 matrix. Okay, so this method holds for any n cross n. Okay, so for a higher order, okay, so I don't have it here, but I can give that as an exercise to you guys. Okay, so it's essentially the same thing. So what you'll need to do, so I'll just write them here. So suppose you have a 4 cross 4, so let's say 1 2 3 4 5 6 7 8 2 4 3 1 1 3 4 6, something like this. So let's say if we are not going by the diagonal method, so usually what we'll do, which you have learned in your 11th and 12th, right? So you'll multiply this with this particular matrix, right? So whatever the uh, determinant you will get for this 3 by 3 matrix, that you will multiply, right? So how do you get? So of course, for this 3 by 3 matrix, so you can calculate the determinant, right? So in the case of 4 by 4 matrix, I'll need to calculate a lot of three determinants of 3 cross 3 matrices. Okay, so that is a quite time-taking process, but I guess you guys can definitely experiment with this, and do let me know if you confirm to this particular idea. Okay. Okay, so yeah, this is a time-taking process, but nonetheless, you can definitely verify this, and I'll try to add an example of 4 by 4 cross 4 matrix here. Okay, but the idea is the same. Okay, so here also what you will do, so this is a 4 by 4 matrix. So what you will do, you will copy paste the first 3 rows below this, and then you will do the diagonal operation. Okay, so that will have a lot of components there. Okay, so just try to do those. Okay, so yeah, there is another star method. I'm not discussing this because let's stick to this particular technique. But of course, you can explore the star method. Okay, so just explore this on your time. But yeah, this is not required. So one method, and of course, we know two methods as of now. So one is of course your diagonals method, and the other is the conventional method which we all have learned in schools, right? So especially in Indian schools, they teach you how to calculate the determinant in that particular fashion. Okay, but if we talk about any European schools or anything such, so they stick to, let's say, star method or diagonals method. They're essentially the different ways of doing the same thing. Okay, so yeah, so let's move to the next topic, which is inverse of a matrix. Okay, so this is again a pretty important concept which I did not discuss earlier. Okay, so Shubham is asking, diagonals method, can we take first and third row? Your question is not clear, but if you just practice the diagonal method, I think yeah, that should be fine, right? So that's a very easy enough way to calculate the determinant of a matrix. Okay, so you can yeah do that, and I think yeah, that should not be a problem. Okay, so now we want to talk about the inverse of a matrix. Okay, so of course, if you have a matrix A, which is, let's say, this 3 cross 3 matrix. Okay, so this is a 3 cross 3 matrix, right? So now one important thing, just I want you guys to tell me. Uh, so does determinant exist for a non-square matrix? Can you please let me know over chat? And in fact, I'm asking this question to everyone who is attending the class. So I think everyone can reply over chat, right? So does determinant exist for a non-square matrix? So let's say if I have a matrix of order 4 cross 3, can we get the determinant? Right, so no. So determinant is a particular quantity which can only be calculated for square matrices. I hope yeah, this point is clear to you guys, right? Okay, so the inverse of a matrix is denoted by A, and we write to the on top of it -1. Okay, so here uh, to calculate the inverse, so this is the formula which we'll use. So this is 1 upon determinant of A, right? So you can calculate the determinant of this square matrix, and whenever we are saying that saying about the inverse, we'll always say that yeah, this we're talking about the inverse of a square matrix, right? Because only for the square matrices we can calculate the determinant. Okay, and then we multiply by something called adjoint of A. Okay, so this is called adjoint of A, and we take the transpose of it. Okay, so we call this as adjoint of A. Okay, so this is called adjoint of A, and then of course, as you can see, T, so which is short for transpose. So we'll transpose the adjoint, and yeah, just divide it by the determinant, so that will give us the inverse matrix, right? So let's see how we can calculate the adjoint. Okay, so so okay, so let's move. So you know already how to calculate the determinant, right? So this is what we have learned in school. So this is that way, right? Okay, so this is how we calculate the determinant, right? So now we want to calculate the adjoint of a matrix. Okay, so for the first element, okay, so for this element, so what is the formula? So the formula is so let's say 1 plus so in this case I am focusing on this particular element which is del 1 1, right? So del 1 1 is essentially this first element which is at the first row and the second and the first column, right? So we want to calculate that element. So firstly, what we'll need to do, we'll need to calculate what we call as complementary minor, right? So when you're talking about the first row and the first column, right? So this is the first row and the first column, right? So you discard the first row and the first column, and then you only focus on whatever that is left, right? So we can write in this fashion. So A11, right? So this will be the determinant of uh, this particular matrix, right? So this is called the complementary minor, right? So now let's move ahead. Okay, so all right, so let's move ahead. So in this case, this gives us -3, -0, right? So it's -3, and then in this case, how do we calculate this particular element? So this particular element is calculated in this way, right? So this will be -1. Oh, I'm sorry, right? So this will be -1. So -1, this number is particularly fixed. Okay, so this -1 is not coming from this -1. It's not coming from there. Okay, so yeah, just keep that in mind. Do not confuse. So this -1 will always be there. And what are we adding? So essentially, whatever this 1 is there, right? So we'll add these two values together and then multiply by the complementary minor, which is in this case -3. And this gives us -3, right? Because -1 to the power 2, that is -1 squared is 1. And when we multiply 1 with -3, that is -3 only. Okay. So let's move ahead. So del 21 will be calculated. So del 21. So what are the elements that we need to consider? So so we'll not focus on this second row and the first column, but all the other elements apart from it. Okay. So 2003. So we calculate the determinant of this, right? So this is 6, and then we calculate the adjoint element. So -1 to the power 2 plus 1, right? Because this element is sitting at the second row and the first column, right? So in this way, we calculate del 21. Okay, and similarly, we calculate for A31. So same formula, right? So similarly, we calculate for all such elements, right? We do this for all these elements and we get the adjoint. Okay. So in this case, we get the adjoint. So our inverse will be the transpose of the adjoint. So this is the adjoint of A. You transpose this. So as you can see, the column here has become a row, right? So -602 has become a column here. -404, which is the column, which is the row earlier, has now become the column, right? So we take the transpose of the adjoint and divide it by the determinant of this matrix, which is 8. Okay, and this gives us the inverse. Okay, so you know that, yeah, this is a scalar only, and if you wanted to, yeah, get rid of this, so essentially you need to multiply each element by this value 1 by 8. Okay, and in this way you can calculate the inverse of a matrix. Okay, so can you guys please confirm if you are able to understand the calculation for the inverse of a matrix? So firstly, we'll calculate the adjoint. Okay, we'll calculate the determinant of the matrix. We'll take the transpose of the adjoint and then divide by the determinant which we have calculated. Right. So of course, let's say if you have not been able to understand all the calculations, so this experiment is available in your course dashboard. So you can, of course, you know how to operate with this, right? So you don't have to do anything. You just click on new. So this will generate a new data, and then as you can see, you just move, yeah, increase, just click on the right button, right? Or of course you can go back. Okay, so you can verify what is happening, and yeah, this is how we'll get the inverse of matrix A, right? So in this case, yeah, the and determinant is something else, right? So whenever you click on new, it will generate a new data for you. Okay, so there are a lot of things which we can do, but I hope, yeah, you guys get the basic idea of how to calculate the inverse. Okay. So now let's move on to the next important topic. So this is a very important concept, and I would like to spend a few, at least 20, 30 minutes on this particular topic. Okay. So, so this is the concept of eigenvalues and eigenvector. Okay. So let me just read this. The concept of eigenvectors and eigenvalues, so they have numerous uses. For example, to better understand and visualize linear mappings, to understand the stability of mechanical constructions, for solving systems of differential equations, to recognize images, to interpret and visualize quadratic equations, and for image segmentation. Okay, so especially in the context of machine learning, you will be using the concept of eigenvalues and eigenvectors whenever we talk about uh, concepts like singular value decomposition, right? Or essentially eigenvalue decomposition. So these concepts are used in the algorithm principal component analysis. But of course, there are a different set of algorithms. So yeah, we'll also cover the concept of eigenvalues and eigenvectors when we learn about collaborative filtering, right? So SVD, which is short for singular value decomposition. So that is one of the ways. In fact, truncated SVD is one of the ways in which we can do collaborative filtering, and there we'll use the concept of eigenvalues and eigenvectors, right? So this is a pretty important concept, and in fact, a lot of different algorithms where we'll be using this particular concept, right? So this is really important, and right, so it's not only in NLP. So PCA is principal component analysis. So that is an unsupervised learning algorithm, and there we'll see how we can use the concept of eigenvalue or singular value decomposition, where we'll be using these concepts. Okay, and in fact, it's not restricted to NLP. There are a lot of different machine learning algorithms where these concepts are used. In fact, the idea of singular value decomposition. So I'll just give you an idea. So a singular value decomposition is in a way factorizing a matrix. Okay, so uh, let's say you're given a matrix A. Okay, so we can decompose this matrix into, let's say, some other matrices, let's say B, C, D, in a way similar to how you factorize a number, right? So let's say you have this number 16. So how do you write the prime factorization for this in this particular way? Or maybe let's say if you're talking about 12, you write 2 into 3 into 2, right? In this way, okay, or 2 squared into 3. So you know, from the concept of basic arithmetic, right? So any number can be decomposed into some prime factors, right? So that is what we call as prime factorization. If we extend this concept, or analogously we can say, we can extend this concept for matrices as well. So we can decompose a particular matrix into some constituent matrices. Okay, so those will be the factor matrices. In fact, there is an important algorithm what we call as negative matrix factorization. So there also will, so that is a very important role in machine learning, right? So we'll learn about these algorithms and the usages of these, but you need to just understand this basic analogy, right? So similar to how you factorize or prime factorize a given number, we can also factorize a matrix into constituent matrices. Okay, so this is the basic idea of factorization, and these will be this idea will be used when we talk about SVD in particular. So I'll not be introducing SVD, which is short for singular value decomposition today, but when we actually learn about the algorithm, so in fact PCA, so there will be first encountering this algorithm, and there I'll introduce you to the idea there, right? But there you'll need to understand the concept of eigenvalues and eigenvectors. Okay, so this is a very important concept, because see, in machine learning we're essentially dealing with mostly two-dimensional data, and matrices are ubiquitous when you talk about data science or machine learning. And there when we have matrices, so we need to have very sophisticated and advanced tools of doing matrix algebra. And eigenvalue, the concept of eigenvectors and eigenvalues are really fundamental concepts in your matrix algebra, and those will appear most of the times when you learn about the underlying mathematical machinery of different machine learning algorithms. Okay, and I'm also sure that most of you have done engineering, right? And in the first and second year, they actually teach you basics of these concepts, right? And they in academia, especially in most of the schools and colleges, they don't give you a geometric interpretation of what an eigenvalue or an eigenvector is, right? So I studied in IIT Kharagpur. I had this subject in the first year, so I learned about eigenvalues and eigenvectors, but I never got to understand how can I interpret or visually interpret a particular eigenvalue or what does it mean, right? So I knew the definition that yeah, A V is equal to lambda V. So I was happy with that definition, but the teachers or professors, they never focused on how to visually interpret this particular concept, right? But today we are going to do this, understand the concept totally visually, so that you will have a very good geometric interpretation or intuition to interpret what eigenvalues or eigenvectors are, right? So let's yeah, look at the definition of an eigenvector. Okay, so let A be a square matrix. Okay, so this is very important. Yeah, so you know a square matrix, right? So a square matrix, the number of rows and the columns are equal. So let A be a square matrix, a non-zero column vector V. Okay, so now we're talking about a column vector, so essentially a column matrix essentially. So a non-zero column vector V is called an eigenvector if A multiplied by V is equal to lambda times multiplied by V. Okay, so can let's say V is a vector. So if I multiply any vector with lambda, which is a scalar quantity, what does that do? Okay, so I just want you guys to answer in this Padlet. So I'll just share the link over the chat. Okay, so can you guys please answer this question for me? So you are given a vector. Okay, so when you multiply that vector with a scalar quantity, what happens? Okay, so it's a pretty straightforward concept. So what happens essentially? So if you can write in plain English, that would be great. Okay. Okay. So Chitranjan is saying it stretches the vector. Does it also squeeze the vector in other cases? Chitranjan, can you add that point? Okay. So essentially, when we multiply any vector with a scalar quantity, what happens that the direction of the vector, of course, it can get reversed when you multiply it with a negative scalar quantity, but the resultant vector essentially remains parallel to the original vector. The only difference is that your original vector is stretched or squeezed. Okay. So whenever we multiply a vector with a scalar quantity, the resultant vector is parallel. Either it can be in the same direction or on the opposite direction, but about the magnitude. So essentially, whenever we multiply a vector with a scalar, so it stretches or squeezes the vector. Okay. So if the scalar is, let's say, greater than 1, so it will stretch the vector, that is increase the magnitude of the original vector. And if, let's say, the quantity is between 0 and 1, so it will squeeze the vector. Okay, so the magnitude will decrease. Okay, so this is what we get whenever we multiply a vector with a scalar quantity, right? So now we are on the same page. Okay, so we're talking about the definition of an eigenvector, right? So a non-zero column vector V. Okay, so this vector V is called an eigenvector if A multiplied by V is equal to lambda times V. Okay, so what this means? So this is really important. So AV. So what is AV? So I just want you guys to answer this. Maybe I'll just yeah, clear the Padlet. So I want you guys to yeah, just be involved. So tell me, whenever I say A, so A is a matrix, a square matrix, and V is a column vector or a column matrix essentially, right? So whenever we multiply A with V, what happens? Okay. So whenever we multiply A with V, so what is the change that I can observe? Okay. So okay. So Shriram is saying the transformation into column vector. Okay. A column matrix will get, of course, yeah. So let me also, yeah. So suppose maybe I can use some other color here. Okay. All right. Or maybe I can use yellow. Okay. So let's say you have this matrix A, which is 1, 4, 3, 2. Okay, so this is the matrix A, and you have this vector, let's say 4, 3. So, of course, you know that, yeah, when you multiply this, so this is, of course, a 2 cross 2, and this is a 2 cross 1. So, this will give us a 2 cross 1. So, it will give us a vector only. Okay, so I want you guys to tell me. So whenever you see anything as such, okay. So how do you interpret this geometrically, or you, let's say if you're not to say that, yeah, we are multiplying a matrix with a vector. Okay, what else can you say about this? Okay, so this particular operation. Okay, so I just want to know from you what is the geometric understanding you have at this point, right? So. So a linear transformation, okay, that's great. All right. Okay, so maybe I can, yeah, just scroll down a bit and see what the other guys are writing. Okay. So I got this particular term from Sri Ram. So he's saying linear transformation. Okay. So today you'll towards the end of the lecture you'll think about matrix in a very different way. Okay, that I'm pretty sure. Okay, so it's a transformation. Okay, so Rohan is also saying that particular term transformation, which I actually wanted to get from you guys. Okay, so at least few people got it. So uh, okay, so here this. So whenever you think of a matrix, and let's say if you multiply a matrix with a vector, okay, so I wrote something like A V. Okay, so I wrote something like A V, and let's say A was I wrote something like A423, and then this vector was 10. Okay, so so essentially what we can, and let's say this gives us some matrix, so maybe we can calculate that. So 1 into 1 plus 4 into 0, so that is 1. Sorry, so 1 into 1 plus 4 into 0 is 1, 2 into 1 plus 3 into 0 is 2. Okay, so this was the vector. Okay, so this was the vector. Okay, this was the vector. I multiplied this vector with this matrix and I got this particular vector. Okay, so I got this particular vector. Okay, so what does this mean? So you can think of this particular matrix as some sort of transformation that we applied on this particular vector and we got this particular resultant vector. Okay, so this is what I want you guys to always think about matrices, right? So this particular matrix is essentially applying, is equivalent to applying a transformation on this particular vector, which gives us some resultant vector. Okay, so multiplying a matrix with a vector is nothing but doing some transformation on a vector. Okay, so maybe, yeah, I'll so let me just open something. So yeah, I'll just drop, yeah, delete this, and maybe I'll just choose some background so that yeah I can, yeah, maybe yeah, I'll just choose some nice wallpaper. Let's say solid colors. So let's keep something whitish. Yeah, I think this should be fine. Okay. Yeah, I hope yeah you most of you are happy with this color. Uh, okay. In fact, I actually wanted to use some different annotation here. Okay, so what we can do. So all right, okay, don't worry about it. I can use the zoom annotator. Okay, so let's in fact I'll use a different color so that yeah it gets highlighted. Okay, so now let's consider a coordinate system in which we have the x-axis and we have the y-axis. Okay, so let's say, so there is a vector, okay, and this vector, so of course this point is 1 0, and so this is the vector and we can denote this vector as, so for example this is, this particular point is 1 and this particular point is also 1, so this vector can be denoted as 1 1. Okay, so the x component and the y component. Okay, so let's call this vector a. Okay, so now I want to reflect this vector uh, along x-axis. Okay, so I want to find the reflection of this vector uh, uh, about x-axis. Okay, so what will be the reflection? So the reflection will be, in fact, I can use a different color so that yeah, you can. So this is the reflection that we'll be getting. Okay, so maybe I can. So this is the reflection we'll be getting. So now let's call this as a let's say reflection. Okay, so this vector, can you tell me what this vector will be? Just you can write over chat. Okay, so don't write over the Padlet, just let me know over chat. So 1 comma minus 1. Okay, so this is sorry, so this is 1 and then this is minus 1. Okay, so now let's say I set up this question for you. Okay, so let's say you need to find this matrix A on, so if I multiply this matrix on this vector A, I'll get this matrix A reflected. Okay, so can you tell me any 2 cross 2, of course that will, A will be a 2 cross 2 matrix, so can you tell me what A this particular matrix A will be? So I just want to know from you guys. So what maybe you can also scribble over the Padlet only. So I'll just delete your answers and so you can scribble over the Padlet itself. Okay, for now. Okay, so I have given you the problem statement, right? So you need to find this vector matrix A, which when we apply on A, this vector A will get the reflected A. Okay, which is, so okay, so what is the matrix that we'll get? Okay, so Snoti is saying, so we can have something like 1 or maybe, okay, I'll wait for you guys to answer. So just if you don't know, so just try to yeah make a guess. So see, Prashant Jha also came up with a matrix. Okay, so we'll evaluate these metrics. Okay, so Priyanshi also has an answer. Okay, so I'll keep this particular matrix in mind. So 1 0 0 minus 1. Okay, okay, so can you guys yeah delete your post from the Padlet? Now let me just yeah just delete your post, so you can just click on the dot, 3 dots. Yeah, just delete your post from the Padlet. Okay, so yeah, Himanshu, Sriram, yeah, Prashant, yeah, just delete this, delete your post. So now I have this particular, okay, Sheers and Chitranjan, yeah. Okay, now perfect. So a few people said that we can have something like 1 0 0 minus 1. Okay, so this could be a candidate matrix. So let's verify. Okay, so what was, so we needed to find a matrix A, which when applied on this vector A will give us the reflected vector along the x-axis. So let's multiply this with A. So let's see what we get. Okay, so 1 into 1 plus 0 into 1, that is 1. 0 into 1 plus minus 1 into 1, that is minus 1, which is the same as our reflected vector. Okay, so this is a candidate matrix. Okay, so here what we did, so we multiplied this matrix A with a vector A, okay, and we got this reflected vector along the x-axis. Okay, so essentially what we can say about this particular matrix, so this is a matrix which induces a transformation which is equivalent to a reflection along x-axis or reflection about x-axis. Okay, so think of a matrix always in terms of a transformation. So matrix is not just a bunch of or an array of numbers, but a matrix is actually inducing some transformation. So if you are multiplying A with B, okay, so essentially A is a transformation which is being applied on B, and that gives us another matrix C. Okay, so in this case A is not only, it's not a simple, it's not a matrix, but essentially it's doing or inducing some transformation on A, which is giving us the reflected vector along the x, about the x-axis. Okay, so this matrix is essentially doing this transformation of reflection about x-axis. Okay, so about x-axis. Okay, so I hope, yeah, you guys get the idea. Sorry. So maybe I'll just, yeah, delete these. Okay. Okay. So this was the reflected vector we had. Okay. So this was the, and this was the x-axis. Okay. So think of a matrix always in terms of transformation. So a matrix is essentially doing some transformation, or it's equivalent to saying that, yeah, this matrix induces a transformation on this vector to give us another vector, which is in this case a reflected vector. Okay, so now let's change the question a bit. Okay, so I'll just clear all the drawings from here. Okay, so now let's say I want to do the same operation, similar operation. I want to do reflection. So of course, yeah, this is again 1 comma 1. Okay, now what I want to do, I want to get this vector reflected about the y-axis. So what should be the corresponding A? Can you please tell me over the chat? So yeah, please don't use the Padlet. Okay, so let's say this is the A reflected vector. Okay, and this is the vector A. So we want to do the transformation about y-axis. That means, yeah, this will both be the thetas. Okay, so what will be the candidate A or the transformation that we must apply, right? So what is our reflected A? So I'll also write my reflected A, which I want to get. So this is what, -1 and 1. Okay, so this is my reflected vector. So what should be the candidate A? So candidate A, as Himanshu and Sumanta both are saying. So let's see if this makes sense. So -1, 0, 0, 1. Okay, so let's multiply this. So what is it we are getting? So I can write the product here. So -1 into 1 plus 0 into 1, that means -1. Then 0 into 1 plus 1 into 1, that means 1. Okay, so this is the same as this particular vector which we wanted, right? So this matrix is essentially equivalent to applying a transformation which reflects a vector about y-axis, right? So if you apply this or apply this transformation on any vector, it will reflect that vector about y-axis, right? So here, of course, I took an special case of 1 comma 1, but you can do this theoretically for any such vector. Okay, so it will reflect doing this transformation or multiplying that vector with this particular matrix will reflect any such vector about y-axis, right? So we saw an example of a matrix which does or induces a reflection about x-axis. Here now we saw an example of a transformation or a matrix which reflects any vector about y-axis. Okay. Okay, so Chitranjan is saying -1, 0, 1, comma 0. That also works. Would that work for any other vector? So maybe uh, let's say I have 2 here. Okay, so what will be the reflected vector in my case? So -1, comma 2, right? So you are saying that I should have. So maybe let's first check for this particular matrix. So I have 1, comma 2. So this will be -1. Okay, 0, 2. Okay, so this is what I'm getting. But now you are saying that Chitranjan, that we can have this matrix -1, comma 0, 1, 0. So let's see if we get the same thing. Do we get the same thing? No, we don't get, right? So there is a fixed matrix which induces any such transformation, right? Uh, okay, I hope you get the idea, right? So of course, reflection is one such transformation that we can do in any such vector, but there can be gazillions of transformation that we can think of. Okay, so let's think about other transformations. Okay, so let's think about sorry, yeah. So we can have another sort of transformation. So suppose you have this vector A. Okay, so you need to rotate this vector by, let's say, 30 degrees. Okay, so this will be something A dash. Okay, this vector could be anything. So maybe I can just write A1, A2 here, and of course A dash could be anything else. Let's say A1 dash, A2 dash. Okay, so let's say you want to do a transformation on a vector A which rotates this vector by 30 degrees. Okay, which 30 degrees in fact, which direction? Counterclockwise direction. Okay, so there you can find a matrix A which, when multiplied or applied on A, gives us this rotated vector. Okay, so whenever we are talking about rotation, so the magnitude of the vector is not changing, but only the direction of this vector is changing. Okay, so we can find a matrix A which does this basic transformation. Okay, we can think about others. So let's say there could be another matrix A dash. Okay, which rotates this vector A, uh, let's say in counterclockwise direction by, let's say, 45 degrees, something like this, right? So there are numerous such transformations possible. There could also be such transformation in which you have this vector A, so it not only rotates the vector but also changes the magnitude, right? So that is what we also call as shear, right? You must have learned about shear if you are doing mechanics, right? So we know about shear, right? So essentially there is not only rotation, but there is also uh, the stretching or the squeezing, right? So the length of the vector in the case of shear transformation, so it's not so the magnitude is also changing, the direction is also changing, right? So the whole idea of discussing all these things is to say to you that always think of a matrix as similar to applying a transformation on a vector which gives you another vector. Okay, in this case. Okay, so what are eigenvectors? So I'll come back to, so eigenvectors. Of course, I can write the definition. So for the definition of eigenvector is, let's say if you have any matrix or equivalently any transformation which you apply on a vector V, so this will give us another vector which is, so this vector is just the scaled version of V, right? So there is a matrix A. What it does not rotate the vector. What it only does, it stretches or squeezes the vector. Okay, so any such vector will be called an eigenvector. uh, so what we'll say exactly, so let me just yeah, go back here. So a non-zero column vector V, or this vector V will be called an eigenvector of this transformation A. Okay, so this is really important. So what we'll say that this vector V, this V is an eigenvector of the transformation. Okay, so transformation, of course I'm writing in short, so transformation A, which results in only scaling of that vector. Okay, so this is very important, and you should understand what it geometrically means, right? So I told you that, yeah, if you multiply any matrix on a vector, it does some transformation. So we saw example of reflection, we saw example of rotation, but there is such a special transformation which we can apply on a vector V, such that the resultant vector is only stretched or squeezed. Okay, so this is what we'll call as an eigenvector of this transformation A, because this transformation A will be fixed, okay, which will result in this particular scaling of that vector. Okay, so let's have a look at the visualization, and I think, yeah, you guys will be able to relate to this. Okay, so here I have this transformation, so instead of A, I'm calling this T, which is short for transformation. Okay, and maybe I can, yeah, just what I can do. So I'll apply this transformation T. Maybe what I can do. So, sorry. Okay. So now I can show you the eigenvectors. So eigenvectors are these green ones. Okay. So it's a very interesting concept. So let's say if I have any vector A, okay, I apply this transformation. Okay. So I think, yeah, you guys can see that, yeah, this vector A is nothing but, so let me just annotate this here. So this vector is nothing but 1, 1. Okay, so let's apply this transformation 2, minus 2, minus 1, 2. Of course, I can play around with these numbers. But for now, yeah, just let's stick with these numbers. So I multiply this particular matrix with this particular vector. Okay, so let's see what we get. So 2 into 1 plus minus 2 into 1, that is 0. Minus 1 into 1 plus 2 into 1, so this is 0, 1, right? So which is this transformed vector, right? So T of A is essentially this transformed vector, and A is essentially your this vector on which we are applying this transformation, right? So okay, so for any such vector, so maybe let's say if we talk about A here, so if you apply this transformation on A, so this transformed vector will be this particular one. But now there's very interesting going on here for the green vectors here. Okay, so let's say I move this A and place this on this particular green one. So now, as you can see, so this TA is also along this vector. So what this means, that TA is now just a scaled version of this vector A, right? So if you talk about any such vector, right, so applying this transformation, not only, let's say, rotates this vector, okay, so it not only rotates this vector, okay, just hang on, okay, so it not only rotates this vector but also changes the magnitude, okay, but if you think about these green vectors, so here if I place A, so my transformed vector is just getting scaled or squeezed, right? So in this particular case, it's getting stretched, but in this case, my transformed vector is getting squeezed. Okay, so this means that this transformation, for this transformation, these two vectors, right? These two vectors are eigenvectors. Okay, so these two vectors will be called eigenvectors of this transformation T. Okay, and the eigenvalues will be these values, right? So I'm not going into the detail how to calculate it. Maybe I can yeah, write that formula for you guys, so that yeah, you understand this. But for now, yeah, let me just plug in the other numbers. So maybe I can have, let's say, 1 here, and I can have 1 here. Okay, so reset. Okay, so no, so it's saying no real eigenvalues, no real eigenvector. So for this, there does not exist. So maybe I'll try to change this. So apply t. So for this also, there's no real eigenvalue. So maybe I'll have 1 here. What about this? Okay, so now this has right? So so if you think about this vector A, right? So if we apply this transformation on this vector A, so my transformed vector is now lying along the negative x axis. Okay, but if I place this vector here along the green line, so you can say, you can see that yeah, the transformed vector is this one, but now this is getting squeezed. Okay, so this is just a scaled version, right? So these green vectors will call as the eigenvector of this transformation T. Okay, so yeah, I'll just yeah, pick A and place this over here. So here also on the green one, if I place, so my transformed vector and the original vector A, they are in the same direction, but it's just a scale. The transformed vector is just a scaled version of my original vector. But you can check for any other uh, vector, right? So that is not the case, right? So either my transformed vector is getting rotated, or it also is getting rotated and magnitude is getting changed. Okay, but in the case of, if we are saying that yeah, this is an eigenvector, let's say this is an eigenvector, that means the transformation which is being applied is only resulting in the stretching or squeezing of my original vector. Okay, so how do we say, or how do we code this? So whenever we have a v is equal to lambda v, so we'll say that v is an eigenvector of this transformation A, which results in only the scaling of this vector v. So scaling means it can be stretched or it can be squeezed. Okay, so so Sumanta is saying, what is this rectangle? Okay, so the rectangle essentially denotes this transformation in a way. Okay, so yeah, don't worry about the rectangle. Just focus on how the transformations are happening. Okay, so can you guys please let me know if you are able to understand what an eigenvector is? I'll come to the part where we can calculate the eigenvalues, but can you please let me know if you are able to understand what eigenvectors are? Okay, so even if you have an inch of doubt, please do let me know, so that yeah, I can explain it again, right? So when you think about a matrix multiplication or matrix as applying a transformation, so now you can visualize a lot of things, right? So you saw that when we talked about reflection or rotation, so those are essentially transformations on a vector. So eigenvector is essentially a very special vector. uh, so any vector will be called an eigenvector for a transformation T, such that the transformation results in only the scaling or scaling of that original vector. Okay, so this is the definition you have to understand and remember, right? So here, whenever you're saying that yeah, V is an eigenvector, so you also need to say that V is an eigenvector of transformation T. Okay, because if I change the transformation, my eigenvectors will change. Okay, so let's say if I change this to 3, so yeah, eigenvectors will change, right? As you can see, my eigenvectors are getting changed. Okay, so you can experiment around with this applet, and you'll be able to visualize how we can what are eigenvectors. Okay, I have attached an additional material in your course dashboard where you can go through the exact calculation of the eigenvectors and eigenvalues, but I'll just discuss a basic definition of how to calculate, or how we can calculate the eigenvalues. Okay, so essentially, so what we are saying that AV is equal to lambda V. Okay, so we can also write AV, uh, we can also write AV minus lambda V is equal to a 0 or null matrix. Okay, and now if I take V common, so I can write A minus lambda I, which is the identity matrix, and V, and this is the null matrix. Okay, so to find the eigenvalues which are lambda, essentially the root, whatever equation we'll get, the roots of that equation will give us the eigenvalues. So how do we calculate the eigenvalue? So I'll not tell you why exactly we are doing this, but this is the way. Of course, you can read about in detail, or we can have a discussion offline. But the way to calculate the eigenvalues is you essentially calculate the determinant of this matrix and set this to 0. Okay, so maybe let's go to this point, right? So here we have 3 1 1 1. Okay, so how do we calculate the eigenvalue for this? So we can calculate, so 3 1 1 1, and then we have to multiply by the in fact I'll just erase these. So how can we calculate the eigenvalues? Okay, so now I'll have okay, 1, because I'm dealing with a 2 by 2 matrix, so I only need to have a 2 cross 2 identity matrix. So this is equal to, so the determinant of this particular whole matrix will be equal to 0. So firstly I need to find this matrix. So this is 3 minus lambda 1 so 3 minus lambda 1 1 right, and then 1 minus lambda. So this is the matrix. So I can calculate the determinant of this. So determinant of this particular matrix will be 3 minus lambda 1 minus lambda, and then minus 1 into 1, and then I'll equate this to 0, right? Because to calculate the eigenvalues, the determinant has to be equal to 0. We can have this discussion later on why this particular condition is there, why the determinant of this matrix will be 0. But just let's see how we can calculate, right? So I can write this similar as lambda minus 3, lambda minus 1, and then minus 1 is equal to 0, right? Sorry. So this is equal to 0. So here I'll just hop onto the top. So this will be lambda square minus 4 lambda plus 3 minus 1 is equal to 0. Okay, so this is the equation we are getting. So we can write lambda square minus 4 lambda plus 2 is equal to 0. Okay, so let's see what were the eigenvalues. So 2 minus root 2, 2 plus root 2. Okay, so if you calculate for this, you'll get those roots. Okay, so I hope you guys are able to solve a quadratic equation. You can calculate the roots of this equation, and the roots of this equation will be the eigenvalues. Will be the eigenvalues of this transformation A. Okay, so the eigenvalues are essentially corresponding to this transformation A only, right? So I hope you guys are able to understand this particular concept. Okay, can you guys please let me know if you are able to comprehend all of these stuff? So how do we calculate the eigenvalues and what are eigenvectors? Okay, I'll skip the part where we calculate the eigenvectors using the eigenvalues, but that is available in your additional material. So that's a pretty straightforward thing, right? So is essentially solving a linear equation. Okay, so just see how we can calculate the eigenvectors and confirm if those eigenvectors matches with these vectors from your calculation. Okay, so that is sort of an exercise for you guys. So okay, so I hope you guys are able to understand what eigenvectors are and how we can calculate the eigenvalues. So eigenvalues, so wherever you are saying eigenvalues, so it will not be an independent word, but you have to say eigenvalues for this particular transformation. So if I change this transformation, so maybe if I change this to 4, I'll have different set of eigenvalues. Okay, so eigenvalues are very specific to the type of transformation which you're applying. Okay, so I hope you get the idea, and these are your eigenvectors. So these are your eigenvectors, the green ones especially. Okay, but for some cases will there will be no real eigenvalues, right? As in the we got that quadratic equation, right? So that quadratic equation in many cases it will not have real roots, it will have imaginary roots. So in those cases we'll say that it does not have eigenvalues, right? So I don't know if for yeah, so for this particular matrix, so for this particular transformation, so what we'll have, so 2 minus lambda, 1 minus 2, 1 minus lambda, and we'll equate the determinant of this to 0. So what we'll have, so lambda minus 1, lambda minus 2 plus 2 is equal to 0. So lambda square minus 3 lambda plus 2, so plus 2, that's 4. Minus 4 plus 4. I think it has real roots. Did I make any mistake? 2 minus lambda. Did I make any mistake, guys? Because I think, okay, no. So lambda square minus 4 lambda plus 4 is equal to 0, right? So this equation does not have any real roots. Okay, so you can confirm. So this equation does not have any real roots. So that's why there are no real eigenvalues. Okay, so you can do these experiments, and I encourage you guys to play around with this applet and see what are eigenvectors and how you can calculate the eigenvalues, and see if you are able to come up with the eigenvectors, which I have skipped and not discussed, but you can calculate those. Okay, so I hope, yeah, this was an interesting piece of information for you guys. And yeah, let's. So, all right. So, thanks again for joining in today's session. I'll see you guys tomorrow. So, tomorrow, also the maths, essentially, we have covered linear algebra and calculus. And tomorrow will be, you'll be learning about probability theory. And then on Friday, we'll have this lecture on summarizing data. So, how we can get the descriptive statistics or the summary of a data set. Okay, so few concepts we'll introduce, and then on Saturday you'll have a lecture on gradient descent, that is the guided project. There we'll use the concept of calculus and linear algebra, and we'll be implementing that particular algorithm in Python, right? So it essentially includes everything what you need to take out from this week. Okay, so I hope, yeah, you guys are having fun. I'll see you guys around. Okay, so thanks again for joining. Have a good night.